the universe broadened convincingly, empowering out-and-out extra astounding length. After this period, it endured to develop, yet at a more drowsy charge, eventually changing into the universe we take a gander at nowadays. This is the inflationary hypothesis of the collectible cosmic impact, the most extreme, famous and widely sought hypothesis of how the universe began. Anyway, for some physicists, this head theory doesn't precisely paint the development of our universe. They suggested that the universe existed sooner than that, stretching out on and on into the past as well as into the future. While the universe is broadening these days, it became contracting before the Big Bang. In this view, the Big Bang isn't really such a lot of a bang as a bounce, a second when the contracting universe switched ways and headed out to yet again make. As demonstrated by their hypothesis, the universe might need to pass with continued progress, probably not entirely set in stone by a breakdown inside the far future, then another skip. Some physicists propose the universe is most likely endless, thus questioning the standard cosmological view wherein the entire thing started with a huge bang. The astounding physicist Brian Cox also challenges the hypothesis of ways things arrive to put forward that something can't rise up out of nothing. Adding to the tension, the James Webb Telescope has made surprising discoveries conflicting with the idea that the Big Bang can be taken into account as the beginning of the universe. These discoveries bring up the question, if the Big Bang wasn't the beginning of the universe, then what was? Could the universe sometimes start with a sidestep or something else entirely? The possibility that the universe had a starting or a day without a yesterday, since it was first perceived, goes back to Georges Lemaitre in 1927. While it is a not exactly perfect situation to propose that the universe probably had a starting, that length of cosmic history has close to nothing to do with the hot, sizable bang that described our hidden universe. Anyway, a minority of specialists, or even a few specialists, still stay with the belief that the Big Bang denotes the very start of all that matters. Thought about the definition is out of date. The Big Bang isn't the show of presence as we'd be mindful of nowadays. As a matter of fact, there may be a lot of evidence featuring a non-single start of our universe. We never come to those end results dependent absolutely on no prominent end or high temperatures. Our universe is charmingly described by means of an inflationary span that happened before the Big Bang. The Big Bang is the result of what happened toward the culmination of advancement during that time. The universe changed into absolutely void, no flotsam and jetsam, no photons, just void space. Region itself became pressed inside immense measure of power at each spot. This strength changed over time, reaching out in a brief, furthermore, resolved style. In light of the fact that the universe broadened, those adjustments relaxed to enormous augmentations, even as new, restricted scale alterations were made to refine them. This superposition of hazards across scales is a distinguishing point of cosmological expansion. It's random for inconsistent reasons, not purposeful. If you lived in an expanding universe, you'd probably come upon nearby regions in which expansion arrived at an end, or the region between you and them slowed vehemently. In a nutshell, you might try to comprehend what happens towards the beginning of an immense effect before that spot disappeared totally from view. Toward the beginning, it consisted of a little area, potentially not any more critical than a human-sized hamster ball, though probably widely greater. The energy component of region then gets changed over into matter and radiation. This variety happens rapidly, taking generally, but now not quickly, because the energy sure up in region itself changes over into particles, photons, and more, and the temperature quickly increases from a couple of degrees above absolute zero to maybe around 20 Kelvin over the same short period of time. Due to the immense level of power, everything operates close to the speed of light. All garbage acts as radiation with huge strength, whether they're massless or huge. This change is called warming, denoting the finish of improvement and the beginning of the stage referred to as the new Big Bang. As improvement continues, you'll witness an enormous change from all preceding circumstances, while the new Big Bang begins. The expanding universe rapidly slows down after the secret picture of advancement in an inflationary universe. Region extends conclusively, with more distant districts running ceaselessly, while advancement closes and the hot Big Bang begins. More distant regions will subside from you to an ever-increasing degree as time advances. The portion of the universe in which improvement closes sees the expansion rate drop, even as the extending regions surrounding it see no such dip. Under expansion, the space to anything could double after a certain span, and while that identical measure of time slips by, that distance again doubles endlessly. Once the Big Bang starts, this alters, since the expanding universe eases down after the initial 2D of progress. Before the Big Bang, you might experience improvement wiping off with adjoining regions. These locales in which advancement closures will fill up with antimatter and radiation and extend more gradually than the still developing districts, leaving you inside the expanding, nearby standard local area in spacetime. Those locales where warm Big Bangs get up become remote from various areas in which improvement proceeds, meaning they'll quickly retreat from each other's view within the standard inflationary picture. Along these lines, the improvement cost alterations. There is minimal possibility that any universes with discrete warm Big Bangs will ever have connection. The region wherein we come to live gets particularly fortunate, and development comes to an end for us. The energy capability of room itself gets changed over to a warm, thick, and practically uniform expanse of particles, with the only defects and takeoffs from consistency with respect to the quantum fluctuations that existed and have been relaxed across the universe. Sooner or later of advancement, the high-energy quantum fluctuations correspond initially to overdense regions, while the lower energy changes get adjusted into initially underdense districts. Those, trademark as the seeds of gigantic frameworks, we can't see. These density fluctuations are no longer visible these days as they were while the universe was still undergoing the warm Big Bang. There are no apparent engraves we can get access to from that early length. The principal detectable engrave comes from roughly 380,000 years later, after going through great affiliations. Despite the fact that we will extrapolate again to perceive the fundamental density fluctuations, finding something consistent with the account of cosmic advancement, the temperature variances are engraved inside the grandiose microwave background, CMB, providing proof of how the Big Bang started. Anyway, there are various irregularities between the CMB and our contemporary version of cosmology. We are lacking something, and those might be summed up in 4 irregularities. First, on particularly enormous scopes, the universe isn't generally acting as anticipated. The light from the CMB is being lensed through depend among us, and the CMB importance depends. It behaves like an enormous focal point, bowing and changing over the plentifulness of the light in the rear of it. The degree of this lensing isn't steady with our cutting-edge model, addressing an astonishing adventure for cosmology. Furthermore, the 2 features of the equator of the CMB sky have unique, to be expected temperatures, clashing with the assumption for consistency in the universe's earliest stage. The presumption that the universe should have begun dependably leads to several irregularities. Third, the value of the Hubble constant, which describes how rapidly the universe is growing, changes contingent on whether we measure it from the vast microwave background, CMB, or from adjacent stars. On the whole, these inconsistencies suggest we are missing something pivotal in the way we interpret the universe. One proposed solution comes from loop quantum cosmology, which starts from loop quantum gravity. In this structure, gravity itself is comprised of particles referred to as quanta, molding the material of existence. In loop quantum cosmology, there is a littlest size of region, the Planck scale, or 1.0 times 10 to the power of -35 meters. This implies the Big Bang couldn't exist in a universe described through this guideline. Rather, the universe could never have come to a boundlessly little, dense factor close to the Big Bang. In loop quantum cosmology, while the universe became tiny, quantum amendments created a shocking tension, causing a leap instead of a singularity. This shows that our universe might have begun from a former universe that diminished in size and then extended once more, very much like a phoenix rising from the remains. While the idea of a cosmic leap isn't entirely new, loop quantum cosmology offers a mathematical framework to support it. Cyclic time, just like the idea of an infinite leap, is also found in Hindu cosmology, adding weight to this thought. If loop quantum cosmology is correct, the early universe could have had a moderate power and density. This condition could change the CMB, showing up as slight variations in temperature all throughout the sky. These variations, measured through the best power spectrum, should give huge evidence of the universe's establishment and support the possibility of a leap. In general, loop quantum cosmology offers a compelling opportunity to the conventional Big Bang model, potentially settling some of the extensive standing irregularities in cosmology and offering insights into the origins of the universe. It also offers a promising rationale for the third abnormality, the disparity in normal temperatures between the two sides of the equator of the CMB sky. The structure provided by loop quantum cosmology addresses the main peculiarities situated within the CMB, the strange dipoles at large scales and the lensing influence. According to Dr. Venet Goyne of the National Institute of Advanced Research, the likelihood that these inconsistencies aren't just size errors but stem from quantum gravity results early in the universe is real. The possibility that the universe began in a vast skip has been proposed before, but its verification requires standard-size studies. Grandiose differences represent an attempt in this view, as our perceptions can be limited to remarkable pieces of the universe, confusing our ability. Dr. Dwayne Johnson, a co-author of a giant study and a professor at Penn Country School, highlights the difficulty in verifying such speculations due to the huge reach. However, the integration of new possible outcomes, like loop quantum cosmology and its standard implications, holds promise in solving certain cosmological issues. Despite these advances, a massive question remains: did the universe have a start at all? Defenders of the universe having a starting argue that it did, but this raises questions about the nature of the event that began the entire parcel. On the other hand, cyclic cosmology proposes an endless universe, continually present in a process of vast skips. However, physicist William Kenny of the University of Buffalo recognizes an essential flaw in this idea: entropy. The increase of disorder in a system grows with each infinite bob, leading to a constant consumption of usable energy. This entropy explosion suggests a beginning, like a Big Bang, clashing with the idea of an eternal universe. While new cyclic models attempt to resolve this issue through concepts like sweeping reaches between skips to burn off entropy, Kenny's studies suggest that the universe likely had a totally unique start. Kenny's discoveries highlight the ongoing discussion over cyclic universes, prompting further examination of their feasibility. Defenders of cyclic universes have yet to fully address this objection. The scientific conversation around this subject continues to evolve, driven by the quest to determine the universe's beginnings and its ultimate fate. Quantum cosmology and cyclic models, which suggest different mechanisms to address anomalies, have sparked interest among cosmologists. Nelson dos Santos of the Brazilian National Institute for Space Studies, who has explored bouncing and cyclic models, notes that while loop quantum cosmology's bounces address CMB irregularities, they may not be helpful. Still, he remains convinced of the possibility of a cyclic universe. According to Nelson, the existence of the universe is invaluable, making a cyclic universe, always present, seem more plausible than one created at a specific moment. As a researcher, he remains open to exploring both possible outcomes. While the beginning of our universe remains a mystery, there has been intense discourse about its final destiny. The fate of the universe depends on its creation, including dark energy, and determining its destiny is crucial. Essentially, there are two main scenarios: endless expansion or, on the other hand, contraction. In one situation, the universe expands endlessly, with stars eventually depleting their gas, leaving behind celestial remnants like white dwarfs and black holes. But the fate of the universe depends on the nature of dark energy, a mysterious force driving the universe's expansion. If dark energy remains constant, the universe's expansion will accelerate, leading to a cold, dark, big freeze, as stars scatter and entropy increases. On the other hand, if there's enough counteracting force, the universe's expansion may slow and reverse into contraction. This situation leads to the possibility of a cyclic universe model, where the universe goes through cycles of expansion and contraction, never reaching infinite density or a specific beginning. Each cycle marks the start of a new period of life, offering a more comforting view compared to a cold, dark demise. Regardless of the universe's fate, our existence at this moment is precious. It underscores our unique position in the universe and the essential potential of mastery in understanding the universe's infinity and its eventual reality. As we ponder the nature of the universe, we are compelled to remember the significance of our reality and the fleeting nature of time itself. Thank you for observing this episode. Your support helps us deliver high-quality content, and we value your feedback on fresh topics. Stay tuned for future episodes by subscribing and spreading the word. Until next time, keep exploring the mysteries of the universe.